Hi, myself Y Nitish Kumar from ITA section. My topic is singular and non-singular matrix. Matrix. In mathematics, a matrix is a rectangular array or table of numbers, symbols, or expressions arranged in rows and columns, which is used to represent a mathematical object or a property of subject such an object. Without further specifications, matrices represent linear maps and allow explicit computations in linear algebra. Therefore, the study of matrices is a large part of linear algebra, and most properties and operations of abstract linear algebra can be expressed in terms of matrices. For example, matrix multiplication represents composition of linear maps. Not all matrices are related to linear algebra. This is in particular the case in graph theory of incidence matrices and adjacency matrices. This article focuses on matrices related to linear algebra, and unless otherwise specified, all matrices represent linear maps or may be viewed as such. Matrices with the same number of rows and columns play a major role in matrix theory. Square matrices of a given dimension from a non-commutative ring, which is one of the most common examples of a non-commutative ring. The determinant of a square matrix is a number associated to the matrix, which is fundamental for the study of a square matrix. For example, a square matrix is invertible if and only when it has a non-zero determinant, and the eigenvalues of a square matrix are the roots of a polynomial determinant. In geometry, matrices are widely used for specifying and representing geometric transformations and coordinate changes. In numerical analysis, many computational problems are solved by reducing them to a matrix computation, and this involves often to compute with matrices of huge dimension. Matrices are used in most areas of mathematics and most scientific fields, either directly or through their use in geometry and numerical analysis. Non-singular matrix. Non-singular matrix is a square matrix whose determinant is a non-zero value. The non-singular matrix property is to be satisfied to find the inverse of a matrix. Let us learn more about the non-singular matrix, how to find a non-singular matrix properties, examples of the non-singular matrix. A non-singular matrix is a square matrix whose determinant is not equal to zero. The non-singular matrix is an invertible matrix, and its inverse can be computed as it has a determinant value. For square matrix A, the condition of it being a non-singular matrix is the determinant of this matrix A is a non-zero. The determinant of a matrix helps to find if the matrix is a singular matrix or a non-singular matrix. The determinant of a non-singular matrix is a non-zero value. The determinant of a matrix can be calculated through row or column operations or by finding the determinant using the cofactor of the elements of the matrix. Properties of non-singular matrix. The following are some of the important properties of a non-singular matrix. The determinant of a non-singular matrix is a non-zero value. The non-singular matrix is also called an invertible matrix because its determinant can be computed. The non-singular matrix is also called an invertible matrix because its determinant value can be computed. The non-singular matrix is a square matrix because determinants can be calculated only for non-singular matrices. The product of two non-singular matrices is a non-singular matrix. If A is a non-singular matrix, K is a constant, then Ka is also a non-singular matrix. Cofactor. The cofactor of an element is calculated by multiplying the minor with 1 to the exponent of the sum of the row and column elements in order representation of that element. Determinant. The determinant of a matrix is the single unique value representation of a matrix. The determinant of the matrix can be calculated with reference to any row or column of the given matrix. The determinant of the matrix is equal to the summation of the product of the elements and its cofactors of a particular row or column of the matrix. Inverse of a matrix. The inverse of a matrix is another matrix with on multiplication with the given matrix gives the multiplicative identity. For a matrix of order 2 into 2, the general formula for the inverse of matrix is equal to the adjoint of a matrix divided by the determinant of a matrix. A matrix is a rectangular array of numbers or symbols which are generally arranged in rows and columns. The order of the matrix is defined as the number of rows and columns. The entries are the numbers in the matrix, and each number is known as an element. The plural of matrix is matrices. Size of a matrix is referred to as n by m matrix and is written as n into m, where n is the number of rows and m is the number of columns. For example, we have a 3 by 2 matrix that because the number of rows here is equal to 3 and the number of columns is equal to 2. Based on its definition, these are some singular matrix properties. Singular matrices are all square matrices. A singular matrix determinant is zero. A singular matrix is a null matrix of any order. A singular matrix inverse is not specified, making it non-invertible. In a matrix, parity subdeterminants. If any two rows or columns are identical, the determinant is zero and the matrix is singular. If all of a row or column's elements are zeros, the determinant is zero and the matrix is singular. The determinant is zero and the matrix is singular if one of the rows is a scalar multiple of the other row. A singular matrix rank is significantly lower than the matrix order. A 3 into 3 matrix, for example, has a rank of less than 3. Steps to find the determinant of a matrix. Before we know how to check whether a matrix is singular or not, we need to know how to calculate the determinant of a matrix. For 2 by 2 matrix, step 1. First of all, check whether the matrix is a square matrix or not. Step 2. For a 2 by 2 matrix, 2 rows and 2 columns. Step 3. The determinant of a matrix A equal to AD minus BC and is represented by mod A. Step 4. The determinant of matrix A equals to A times B minus B times C. Step 5. If the value of the determinant AD minus BC equals to 0, then the matrix A is said to be a singular. Step 6. If the value of the determinant AD minus BC equals to 0, then the matrix A is said to be non-singular. It is sometimes necessary to find a non-zero vector that, when multiplied by a square matrix, will give us back a multiple of the vector. This non-zero vector is called an eigenvector. Eigenvectors are not only of interest to mathematics but to others in professions such as physics and engineering. To calculate them, you will need to understand matrix algebra and determinants. Learn and understand the definition of an eigenvector. It is found for an n into n square matrix A and also a scalar eigenvalue called lambda. Lambda is represented by the Greek letter, but here we will abbreviate it to L. If there is a non-zero vector x, where Ax equals to Lx, this vector is x, vector x is an eigenvalue of A. A non-singular matrix is a square one whose determinant is not zero. The rank of a matrix is equal to the order of the largest non-singular submatrix of A. It follows that a non-singular square matrix of n has a rank of n. Thus, a non-singular matrix is also known as a full rank matrix for m non-square of A of m into n, where m greater than n. Full rank means only n columns are independent. There are many other ways to describe the rank of a matrix. In linear algebra, it is possible to show that all these are effectively the same. For example, the rank of a matrix can be said as the number of independent rows or columns. The matrix has alternatively, the rank is the number of non-zero of the matrix after Gaussian elimination. For an MDOF structural system, usually the mass matrix is the full rank matrix. The stiffness matrix is the same if the system is not allowed to have rigid body motion. A damping matrix that represents damping at a few isolated degrees of freedom will have a space matrix that is not of full rank. If the system does not have repeated eigenvalues, the mode-shaped matrix is a full rank matrix. The coefficient matrix C should be non-singular matrix, and the calculation results tend to come under the influence of a misalignment and measurement errors of each sensors when the matrix C is near a singular point. Since we use the platform as not an actuator but a base structure of measuring instrument, we found the optimal structure based on Stewart platform to reduce the influence of misalignment. Two plates are in a direction parallel each other. The center line, which connects centers of plate, is vertical to both plates, and nodes are placed evenly spaced apart. In this time, we calculate a normalized radius of upper plate R and normalized distance between two plates, which according the center line, when bottom plate radius is fixed to 1 by adding virtual error to the acceleration of up to 10%. The set of calculated accelerations from equation 5 and the average of evaluation values calculated from equation 6 were obtained. The optimal radius of upper plate R and the optimum distance between both plates H were found out by making average value of S minimum. Calculated results were shown in figure 3. As R and H increased or decreased from the optimum value, the average of evaluation value is increased. Because the coefficient matrix became close to the singular point, the calculation results tended to come under the influence of order error. After searching optimum values, the optimum radius of upper plate R should be 0.83 and the optimum distance between two plates H should be 0.93. On the optimum structure with these parameters, the angle made by each link and each place was 43 degrees. Thank you. This is my presentation.